So here let's look at log. We've been working with natural log. Let's talk about how that relates to log as in L-O-G. All right, first of all, a logarithm is an exponent. All right, so if I were to write this true equation that 2 to the 4th equals 16, if I wanted to express that using logs, right, I have this smaller number called the base. Then I have a value here equals some number. All right, so take a minute and try to fill in what you would have in these boxes. And I'm hoping you recognize that this would be log base 2 of 16 is equal to 4. So like I said, logarithms are an exponent, right? So the answer is the exponent, right? And my base goes down here in the little subscript, all right? And so that's how I write these equivalent expressions. Now, if I were to take the equation log base 3 x equals y, right? If I were to write that in exponential form, notice my base is 3, my exponent is y, or I'm sorry, wait a minute, this would be, yes, that's right, and then this would be equal to x. Yes, my exponent is y. So notice on the homework the other night, you were just graphing things that looked like similar to this, except you were graphing y equals 3 to the x. All right, so the only thing that's different about these two equations is I have switched x and y. And I think you know enough about functions to know that when we switch x and y, we get an inverse function, right? So these are inverses of one another, and these two equations are equivalent, right? So the inverse function of y equals 3 to the x is log base 3x equals y. All right, so what that means is when you were graphing this function the other night on the homework, all right, so you had things like this drawn, right? So all exponential functions go through the point 0, 1. Right, so you had y equals 3 to the x. So if I took that and reflected it through the line y equals x, so again, this would go through the point 1, 0, and this would be the graph of y equals log base 3x. So let's look at how log relates to natural log. All right, and your high school teacher probably told you certain things that I'm going to touch on again. But if we were to look at y equals log base a x, using what we established above, then a to the y equals x. All right, so if I wanted to solve that for y, what I could do is take the natural log of both sides to get y alone. So doing that, the natural log of a to the y equals the natural log x. All right, so drop that y in front using the properties of natural logs. And notice that y is equal to natural log x over natural log a. So that's nice to know, because then if I want to say, if I'm more comfortable working with natural logs, right, and I gave you something like this, then you could say, all right, if I want that written as a natural log instead, then this is equal to natural log x over natural log 8. And so when we start taking derivatives, you could memorize a rule for finding the derivative of a log. But I encourage students to write it in terms of natural log. We already know how to find the derivative of natural log. But let me just make one other point before we do some examples with derivatives. Your high school teacher probably taught you, in discussing natural log and E, you probably at some point were told this, that the natural log is equal to log base E of x. And if I want to verify that, I can do what I just established, where log base E x is equal to natural log x over natural log of E, which we know natural log of E is 1. All right, so this was probably a definition that your high school teacher gave you at some point, right? That log to the base E x is equal to natural log x. Now, moving on and doing some derivatives then. Let's say I wanted to find the derivative of this function. All right, y equals log to the base 5 of x squared plus 1. All right, so I know a rule for finding derivatives of natural log. So why don't I write this in terms of natural log then? And when I do that, I get natural log of x squared plus 1 over natural log of 5. So now I'm ready to take the derivative. And sometimes students look at this and say, oh, don't I need the quotient rule? But actually, natural log of 5 is a constant, right? That's just a, that would have some decimal value, right? So what I can do, and I think it'll help you to see this if I write this ratio like this, that this is 1 over the natural log of 5 times natural log of x squared plus 1, right? Because I have a rule from Calc 1 that tells me that what I can do is take my constant, right? Separate my constant, do my calculus, and then multiply my constant at the end. That's called the constant multiple rule. So I'm ready now to find the derivative. So I keep my constant here. Some people say, oh, isn't the derivative of a constant 0? But remember, this is a product, right? So if I were adding a constant, if I had a constant all by itself, then its derivative is 0. But when it's a function times a product, or I'm sorry, I'm saying that wrong. When it's a function times a constant, right, then that's where I push the constant off the side, take the derivative of the function, multiply the constant back in. So the derivative of natural log x squared plus 1, so I do the reciprocal of the function times the derivative of the function. All right, so I would write this as 2x over natural log 5 times x squared plus 1 for my final answer. Now let's look at an integral. So let's try integrating this function. So again, I have log base 8x. And I'm going to feel more comfortable if I have this written as a natural log. So I'm going to come over here and I'm going to write log base a x as natural log x over natural log 8. And maybe I'll take this function and I'm just going to write things separately. Notice how I'm just writing this as an equivalent product. That might help you a little better to see how I'm going to manipulate the pieces. But I have 1 over, I have the reciprocal of log base 8 of x. So if I want to substitute that with its equal, I could substitute in the reciprocal of this fraction, right? So the reciprocal, that just means flip it, right? So I would have 1 over x times natural log 8. Natural log 8 is a constant. I could move that out in front. Dx. All right, so now I'm going to put that constant out in front, right? Natural log 8 is going out in front. And then I'm going to use u substitution. All right, so I'm actually going to let u equal natural log x. And the reason that that will work is because I see the derivative of natural log x as part of my integrand. All right, so I'm going to be able to replace this and this with du, and I'll be able to replace this, right, 1 over natural log, I'll be able to replace that with 1 over u. All right, so the natural log of 8 went out in front. I have 1 over u du, right, by the time I substitute for everything. So I want to make it clear. Students sometimes think, you know, things are just vanishing, right? These don't just vanish. I substitute for them, right? Because I have a statement right here that says that 1 over x dx is equal to du, right? So I substitute for du. And then u is equal to natural log, so I substitute for it. And then we know that this antiderivative is natural log of absolute value of u plus c. And this answer is going to look very strange because u is natural log x. All right, so this might seem like a strange looking final answer, but I get that. Substitute back in for u, and there's my final answer.